Thank you, and thanks for coming. And my apology for being late. I took the wrong turn after getting my coffee, and so much for being a geologist, right? But I ran out of bad lands and said, okay, I'm in the wrong way here. So anyway, yes, my colleague Steve Grasby is a big part of it. He's a geologist at the Geological Survey of Canada, and Steve and I, ever since 1999, we've been going up north to address the issue of the Permian-Triassic boundary. It's been a very, very fruitful collaboration. We published 8 papers on the topic, and we have 2 being reviewed, and some pretty major publications here, 2 of which are just out in geology this very month. So very exciting stuff that we've been able to put together. So my talk here is about the greatest mass extinction in Earth history. You certainly know about dinosaurs in this place here. There's great experts in this organization, this very fine museum, about how the dinosaurs evolved and became extinct. Well, I'm going to talk about something that happened 252 million years ago as opposed to 65 million years ago. I'll talk first about the Arctic record of the Permian-Triassic boundary and how we had to part with an old dogma in order to be able to move forward with our research. Then I'll talk about a long lead-up time in tens of millions of years prior to the extinction, and more specifically work we've done putting concept of anoxia and ocean acidification forward. And then we'll talk about the catastrophe itself, which is related to the Siberian Traps eruption. We'll talk about that and global warming. And then the aftermath, and I will show you how several attempts to recover the biological system were aborted, and I'll tell you why. And then we'll reach some conclusions. So should be able to go through that in about 45 minutes. So the greatest mass extinction on Earth, right? And you know that one, right? And you know the dinosaur vanished, and you know the consensus revolves pretty much around a bolide, a meteorite, hitting planet Earth in an area. This is now a Yucatan Peninsula. And Mayhem just followed suit and killed all these magnificent reptiles. So you know all about that here, probably a lot more than I do myself. You probably also know that there are 5 big extinctions in Earth history. In this diagram here, you've got extinction intensity in percent and in millions of years. So we're here 0, and we go all the way down to the base Cambrian here. And there are 5 big ones. Of those 5 big ones, of course, you have the end Cretaceous here, right there. But the biggest of them all, the granddaddy of them all, is the end Permian right here. And you can see how it peaks here. This blue column goes through the sky, essentially. Now, no matter how you put it, whether you count the number of families or the number of genera, this is by far the largest mass extinction on Earth. Numbers that have been thrown are around that 90 to 95% of at least calcite or calcium carbonate secreting organisms vanished rather rapidly. And also a lot of the non-calcareous life forms as well, because following the extinction itself, there's just very, very little in terms of any evidence of soft or hard bodies. So it's a massive, massive catastrophe that affected planet Earth, and in fact, which pretty much reset the evolutionary clock of our planet. And then after that, there was a lot more origination of species and genera and families, leading to where we are right now. Now, what caused the Permian-Triassic extinction is a cause of debate, and there's really no kill mechanism, and this one is not it. I mean, it's been proposed by some people in Australia based on very sketchy evidence that have been proven wrong, that bolide had hit the Earth, but there's just no crater, none of the geochemical anomalies we associate with such a thing in the Cretaceous, at the end of the Cretaceous. So this is one reason why my colleague Steve Grasby and I went to the Arctic to actually see what was there in terms of the Permian-Triassic boundary, because we knew we had Permian rocks, we knew we had Triassic rocks, and we felt that it should be a good Permian-Triassic boundary section, at least one. And we, as you will see, we found a lot more than one. But in order to do that, we had to part with an old dogma. Now, as François said, I worked for 18 years with the Geological Survey of Canada in Calgary. Great place to work. They funded my research, my Ph.D., and all of this over the years. I cannot be more grateful. But when I got there were giants. You know, when you say we stand on the shoulders of giants, and nothing can be more true than with the Geological Survey of Canada. Especially when you go that far north. This is the area I will be talking about here. It's called the Sverdrup Basin. It's a huge sedimentary basins in the northern part of Canada. It's a petroleum-rich province. It's been drilled in the 60s and 70s, early 80s. Oil and gas fields have been discovered. But more importantly, there's beautiful mountains in the east here that allows us to see the stratigraphic succession in an environment where there's no vegetation. So it's pretty much a geological paradise. Of course, we got there with Twin Otter. This is Ken Borak Twin Otter, very much like the one that crashed in Antarctica a couple of weeks ago, unfortunately. And we certainly know these pilots very well. They are amazing pilots. They can land anywhere on half-deflated balloon tires, on the tundra, uphill, downhill. It's absolutely amazing what they can do. And they set us in the middle of nowhere. And then, of course, with teams of students, we get a helicopter there, and we sling our stuff, set up camp in absolutely pristine, remarkable places to do geology. This is one of my students here, kitchen tent there, private quarters, my tent here. And it's called snoring distance, you know. And the students decide that, not me. So anyway, we do a lot of walking, as you can see, and so you have to be in pretty good shape to be there. And we walk and we wade rivers, and we reach these beautiful outcrops, often polished by retreating glaciers and all of it. As I said, this is geological paradise, where Permian and Triassic rocks are superbly exposed. So sometimes you run into friendly animals. This is Perry caribou, of course. We also carry a gun in case we meet a big white furry thing, but in 30 years I haven't seen a single polar bear, nor tracks, nor turds, nor nothing. So I've been pretty lucky. So students are keen, but just like anybody else, they have to stop for lunch and grab samples. But essentially the geology we do is the same that my former colleagues of the Geological Survey of Canada were doing 40 or 50 years ago. You take notes, you collect samples, you look for fossils, ages, and all of that. The technology has not changed. The science has not changed. Now we use GPS. We know exactly where we are. We have satellite phones and all of this, but it doesn't change anything to the geology. 50 years earlier, these people didn't have a team of 12 or 13 grad students like I do. They were actually two giants of Canadian geoscience, Ray Thorsteinson, who unfortunately passed away earlier this year, and Tim Tozer, who passed away a few years ago. Alone, these two guys pretty much mapped the entire Arctic and defined the stratigraphy in a basin that was not even known to be there. Like they literally defined the Sverdrup Basin. It's amazing what they did, the amount of work they did. They would go there for 6 months in dog sleds and canoe, and the most amazing winter to winter conditions, essentially, away from their family and everything. But they were passionate geologists, and their contribution to Canadian science is absolutely mind-boggling. Both became, of course, members of the Order of Canada, and were celebrated as a tremendous scientist, as it should. But one thing they did, this is a stratigraphic column here, Carboniferous and Permian, you got a Triassic here, and Ray Thorsteinson, recognized that there were 5 major stratigraphic sequences, and you can see those gaps in time, right? These vertical lines tell you there was a gap in time. At least that was the interpretation. And so we look at this area here. This is the transition from Permian to Triassic. So, and the belief was that the entire late Triassic was missing, late Permian, sorry, and part of the middle Permian was missing. As much as 15 million years worth of time was missing there, according to them, based on ammonoid fauna, right? Or the lack of ammonoid fauna, I shall say. And in the central part of the basin was even more, 20 million years. 20 million years is a lot of time. And because of that, these people and successive generation of geologists at the survey thought that there's no sense studying the Permian-Triassic boundary in the Arctic. It's just not there. Well, these guys had even stronger opinions. This is the famous Tim Tozer, who you can call the father of Triassic ammonoid stratigraphy in the world, celebrated as such. Tim had a very strong opinion based on what he could see in Permian and Triassic ammonoids, that the evidence suggests that the boundary between marine rocks, Permian-Triassic age, invariably marks a hiatus, that means a gap, not only in Canada, but throughout the world. He thought that throughout the world there was a big, big gap, that there was nowhere late Permian or latest Permian rocks to be seen. That's quite a statement. And then it was staying a bit further, the period of time unrepresented by strata could evidently fall within the Permian, not the Triassic. So Tozer became very famous because he set the 4 stages or substages of the early Triassic in the Canadian Arctic. They're called Grasbockian, Dinnerian, Smithian, and Spathian. and they were defined by Tim Tozer, and they're still used to this day as the standard of Triassic time. And here's his final statement here. We are left without any section that clearly provide a transition in the marine fashion between the Permian and the Triassic. That was Tozer's view in 1967. And my dad, was probably his view by the time he died a couple of years ago. Unfortunately, or fortunately, a lot of people took that as a challenge to find those continuous sections around the world, and they did find them. Over the following 40 to 50 years, all around the world, they found succession that were with no evidence of a major gap between the Permian and the Triassic. And some of the best actually were right there in Meishan, South China, which was more near the Paleo equator at the time. This is our Sverdrup Basin there at the time, 250 million, 2 million years ago at the time of the Permian-Triassic extinction. And there they found in one bed, you know, the proper fossils. And those fossils are called conodonts. Conodonts were worm-like animals, little worms that swimming in the ocean. And what is preserved is actually the teeth of these animals. And this is a part of the jaw or the teeth of one of these tiny little worms. And these things have evolved dramatically across the Permian and Triassic boundary. And there's one species called Indiotis parvus, which is recognized now as the marker of the base Triassic around the world. So this is Meishan, China, where what we call the global stratotype line and point is in the rocks here. There's a big theme park and everything there. Unbelievable. The Chinese put a lot of money to put their finger on that boundary, and they got it right, I might add. One thing, though, the mass extinction here, you can see here, get this red arrow, is not at the Permian-Triassic boundary. It's slightly a bit lower. And it doesn't seem like just a few centimeters here, but that few centimeters is as much as 100,000, maybe up to 600,000 years. So this is very, very condensed here in this succession. But the mass extinction is within the late Permian. So now we talk about the latest Permian extinction or the end Permian extinction as opposed to the Permian-Triassic extinction. So something to remember. The extinction is high in the Permian-Triassic boundary is somewhere higher. All right, so let's go to the Sverdrup Basin. This is what we did, Steve Grasby and I, in 1999. We said, listen, you know, everywhere around the world, these Permian-Triassic continuous sections are popping, and we're still sitting in our office in Calgary being told by our masters that don't even bother, we don't have it. And Steve and I just couldn't take that as an answer. This is what young people do. You challenge your masters, right? And I always encourage my students to do that with my own stuff. Well, that's what I did with the stuff of Thor Steinson and Tozer and Nazichuk. And I said, listen, that basin is a big sag basin. It's a big gaping hole there. You can see that. This is slope and basinal facies surrounded by a shallow water carbonate shelf system. So that's like carbonate shelf and surrounding, you know, a deep water hole. Not as deep as the modern ocean, but probably now we know about 1 or 2 kilometers deep. So surely you must have in this area somewhere a continuous section across the Permian-Triassic boundary. It just makes no sense that the whole basin was emptied of its water, you know, 1,000 meters, maybe more worth of water at the end of the Permian. It makes no sense whatsoever, but we had to prove it. So we went to prove that. And first place to prove it was in seismic profile. That's the first thing we did. The industry had shot some seismic in the Western Arctic, Sabine Peninsula and Melville Island. And here you can see these railroad tracks here. They're good carbonates, and they're middle Permian carbonates. So this is where the last fossils, good recognizable fossils that you could date, were found in the Sverdrup Basin. They're ammonoids, they're brachiopods, you know, they're good fossils. But then we were able to prove that you could follow these reflectors, right? And there's actually a very thick late Permian wedge of chert, that's siliceous sediment, right, you know, between those last dated beds and the Permian-Triassic boundary. We're talking as much as 1 kilometer of strata here on this seismic profile. And then when I did my Ph.D. in the mid-80s, I found exactly the same thing in southwest Ellesmere Island. You can see here the Permian-Triassic boundaries at very sharp contact here. This is a blind fjord formation. This is all chert here. And here's the last carbonate, just like we saw on seismic profile. The last carbonates with dated fossils, and they disappear. You know, the carbonates just shale out into a deep water shale, you know, a siltstone. So this is deep water. It shallows up here. But there's another sequence right on top here. This is good, clean, shallow water spiculitic chert. And spicules, I'll show you what a spicule is, essentially a remnant of a siliceous sponge. And then we traced these beds laterally into deeper water. And sure enough, we found some equivalent chert, but this time darker, deeper water. But sure enough, this is the Permian-Triassic boundary right there. The same sequence was there. And we went that way deeper and deeper and deeper and got more and more and more of that succession. So surely it was there. So in one of our recent, the first contribution which Steve and I came out with was to put all the stratigraphy together, and we therefore came up with two different names, new names, to account for that upper Permian sequence that had been ignored by our previous scientists, right? So the Lindstrom formation, that's the white chert going into the black stripe formation, that's the black chert and shale. And we got the fossils as well, again, conodonts with Charles Henderson of the University of Calgary. We sampled like crazy. And now, we're not talking about an environment that's as productive as Meishan, but still, some of the key conodonts are there. We did find a few in the late Permian there that are characteristic. And we found certainly the early Triassic one, including our friend Hindiotis parvis, which is the global marker for the base Triassic, right? And so we put that together, and then we put that in a sequence stratigraphic framework, which means the packages of rocks between those unconformities. And we realized, studying this in great detail with Steve Grasby, we cross-section again from the shallow stuff to the deep water stuff. What Steve and I did after that, just to prove it, we were totally convinced it was continuous, but just to prove it, we used stable isotopes across all these sections here to try to prove that it was continuous sedimentation. So we look at this area here. This is the type section of the Lindstrom formation at Lindstrom Creek. So you can see the white rocks here is very resistant, yucky looking. It's all chert. This thing will rip your boot to shred. They're absolutely full of sponge spicules. In outcrop, this is a finger here, dirty finger. You can see these cross beds here. These are what we call homoky cross-stratified structure. They represent storm deposits. In other words, this is a proof that it was very shallow water, not deep water for that chert. And then this is what the thin section will show. This is what you see under a microscope. You've got little sticks, and these are sponge spicules. I don't have a scale here, but one little stick like this might be 0.5 millimeter long, and you can see how thin they are, but extremely well preserved. You see the internal canals, they're all siliceous. It is pure SiO2, like quartz, but it's actually calcium in a different form of quartz. But that's pretty much all you have in this entire late Permian succession is sponge spicules, right? So everything else had been eradicated. All those calcite-secreting organisms, the brachiopods, the bryozoan, the echinoderm, the ammonoid, everything had been eradicated. No wonder they could not find the right fossils to date the rocks. They weren't just not there. Something bad happened even prior to the late Permian extinction. So the environment here is what we call the glass ramp. It's an environment, this is the shoreline here, and this is the deep water here. And this is an environment, what we call the carbonate factory, was essentially non-existent. It was gone, right? On the other hand, what we call the silica factory was very productive and extended from very shallow water to very deep water, right? All these spicules, all those sponges were happily invading every single ecological niche on that shelf. And it's not just the Sverdrup Basin. This is the Sverdrup Basin here, but it's a phenomenon that we see all along the western margin of what we call Pangaea. Pangaea is the big supercontinent in the late Permian, and we have evidence of that chert all around Western Canada. We've got that here at Banff, for instance, the fantastic chert, the Johnson Canyon, and so on and so forth. And in Svalbard, along with western U.S. here, it's just a hemispheric phenomenon here. All the shelly fossils disappear prior to the late Permian extinction. So the next thing Steve and I did then was to look at the deeper water stuff. We went to that section here, which is a key section. It's called Buchanan Lake. And in there, you're deep water, right? You've got deep water shale below, deep water shale above. We have no evidence of an unconformity. This is what it looks like in the field. We measured a section here, then this is the boundary right there, and then across here, Black Stripe Formation, Blind Fjord. It's all shale. It's all mucky. You'll get on your knees. You get very dirty when you climb something like this, about 400 meters of strata here. And it's not a pristine section, but it's all there. Every single bed is there, and it allowed us to do some tremendous work. At the boundary, we found a 1 centimeter layer of pyrite right there. You can see that the rusty material seeps down and stains the rocks yellow here. Well, that is the event, the catastrophic event I will talk about later. But in that section, it is preserved there. So we ran some stable isotopes, carbon isotopes of organic carbon. So this is just a ratio of carbon 13 to carbon 12. They're just different, well, same element, but different weight because they have different number of neutrons. That's pretty much all we need to know here. But you see here, they're plotted a lot of samples, 600 samples we picked across that cross-section here. And interestingly, in the margin here, we do know that there's a big unconformity. You can see the signal is cut off, right? There's a big kick here. And that kick is not a big event or anything like that. It's just the unconformity. It's just part of the signal is missing because rocks are missing. But when you go offshore towards that Buchanan section where there's nothing missing, you can see here that there's no more separation of a signal, and it's a beautiful continuous signal here. Now, one thing you should know, so here's this and here's that here. One thing you should know is that Permian-Triassic extinction, or latest Permian extinction, is associated with one monster isotopic shift that's very well recorded around the world. This is Meishan here. You see those data there shifting to the left. Same at Gartnerkofel, that's a core in Austria. And here's our Buchanan Lake section. See, that goes just about the same as Gartnerkofel. It goes down and then kaboom, it really, really drops, and then it stays low for a while and it comes back. So this was really the smoking gun for us. We had the proof that we wanted forever, that the succession is continuous, and the isotopic record was providing this to us. There it is. So that was our first big paper, Steve and I, plus the one on the stratigraphy here. So there it is. What we know now is that, yes, there is a big sub-Triassic unconformity or sub-blind fjord unconformity, and it extends quite far into the basin. But if you go into a deeper part of the basin, there's continuous sedimentation and therefore a fabulous Permian-Triassic record. So that was the first conclusion that we had here, that the late Permian or early Triassic transition is well preserved in Arctic Canada. So nothing is missing in the deep basin. Sorry, Thorsteinson, sorry, Tozer, you had it wrong. We have it right. This is how it works. And late Permian sediments are fossil-poor biogenic chert. So don't look for any ammonoids or things that you want to date your rocks with. It's just not there, except for these tiny little phosphatic condoms, right? The only fossil are siliceous sponge spicules, plus those things we can grab in dissolving the rocks, which are phosphatic. All right? All right, so that takes me to the lead-up. Now now that we've set the stratigraphy, we know what we're looking at now. Now let's talk about the extinction. And the lead-up has two big things I want to talk about. One is anoxia, because one big theory about the Permian-Triassic extinction, which has been going on for about 20 years, is that the seawater became depleted in oxygen. And we call that anoxia, lack of oxygen, right? And there's various reasons for that. I'll get into that later. But it's a very, very big idea that still survives to this day. Some people are staunchly believer that is the cause of all the extinction, at least in the ocean, that the ocean became anoxic. So Steve and I went back to Buchanan Lake, our beautiful section, as you can imagine, and we measured, we sampled, like here's our isotopes, but we sampled for other chemical indicators. We also broke our succession to different phases, 1, 2, 3, 4, 5, 6, 7 in Roman numeral here, and keeping our eyes on that boundary, which is the pyrite. You remember the pyrite layer here? That's iron sulfide right there. You've got more iron sulfide higher. You've got some carbonates here. So what we did, we just ran a whole bunch of chemical indicators. And you don't need to be a geochemist here to understand what I'm telling you. I don't even understand it myself. Probably Steve is the expert here. But the key thing here, this is our boundary between the Black Stripe formation and the overlying blind fjord formation. So that is the event. That is the late LP, latest Permian extinction event right there. And you can see a number of indicators. First of all, this is total sulfur here with those pyrite layers. You can see it increases the boundary and then decreases here. This one is molybdenum on aluminum here. You can see it increases to the boundary and decreases again. This one is nickel, right? And decreases. And then finally, chromium. Look at that. That's a beautiful trend, as good as a trend you'll ever get in your life. All of these are indicators of anoxia, because you can only, if you sequestrate those kind of elements in your rocks if the conditions are without oxygen. So those are dead ringer, especially the pyrite layers there of anoxia. So far, we seem to be supporting those guys who believe this is the cause of the extinction. Then we did the same thing here. Here's the boundary here, and we focus on the essentially 10 or 15 meters below and about 15 to 20 meters above. And you can see all these things, all the indicators, and Steve, in very eloquent way, could explain all these things to you. The key thing here is that we believe that through time, this is a time series here from A to J here. So A would be a late Permian, starts in the late Permian. Here would be early Triassic. At true time, you know, sea level has gone up, but also at one point you start developing anoxia in the deep basin, and that anoxia, you know, they started here, and then it got shallower and shallower and shallower, and you reach that peak here right at the extinction level, which is right there. And I'm just going to increase that. This is when the shelf itself, that is the shallow water area where all those fossils should be living, became under not only anoxic condition, but what we call euxinic condition. In other words, there was so little oxygen in the ocean that now pyrite was precipitating right out of seawater and was raining down to the bottom floor, and therefore you see that continuous pyrite layer. There's very few places in the world where we see that right now. One is the Black Sea, where the Black Sea is very stratified, about 200 meters below the surface. You get into very anoxic water and even euxinic water, and pyrite rains down to the bottom. So far, so good. Now, then we took another step with a fellow geochemist from Germany, Joachim Nies, and this time we look at the stable isotopes of nitrogen. So again, very complicated diagrams. Don't worry about them. Myself, I don't understand them all. Couple of things here. One is what we call a lycopene here. It's a biomarker, and then all kinds of indicators of you know, anoxia or various things. And so we looked at this here. This is the isotopes here, the carbon to nitrogen ratio. Very important. So you can see trends here, declines as you go up. And then here we compare those trends here with Meishan. This is Meishan here in China, that global stratotype, and our stuff here. And our stuff is much different than Meishan. It's much lower, and so we were able to actually demonstrate that boundary, you know, what we call the redox boundary that occurs here was actually substantially deeper than we thought. This guy Knies in Germany told us no, it was actually below the photic zone, the zone of light penetration, which means that the top of this here was a good 100 meters below water. So again, it kind of put some doubt into that model that says that anoxic water just killed everything at the end Permian. We seem to have here geochemical evidence that there was actually oxic conditions somewhere on the shelf, not in those sections, but somewhere on the shelf. So then we went on to find those areas where it would have been oxic, and we found one section. It's called Blind Fjord, West Blind Fjord here, and this is a paper that is currently being reviewed, but we use another type of isotopes, molybdenum, and you can see here the red dots are all Buchanan Lake, whereas those yellow squares are from Blind Fjord, and they tell you Blind Fjord was oxic while the rest was anoxic, right? So here we have very good evidence, and we were forced now to change our model a bit, and this time we realized we had an oxygen minimum zone. In other words, there was oxic water at the bottom, but also at the top, and that, as I said, the top of that zone was about 100 meters deep, which means that some large areas were under oxic conditions. So if a large area of shallow water were under oxic condition, therefore, you cannot invoke anoxia as the cause of the extinction. It's probably a contributing factor, but not the cause. So here's some summary of that geochemical work. The late Permian deep to shallow buildup of anoxic waters and latest Permian euxinic conditions in the Sverdrup Basin led to the precipitation of pyrites in seawater, very bad conditions. However, we know that anoxia and euxina occurred in an oxygen minimum zone below the photic zone, below the zone of light penetration, so that's below 100 meters. So this means that large areas of the shelf remain oxic, therefore good for life, right? All right, so the other lead up that we had is ocean acidification, right? You've heard about ocean acidification because we hear about it in the modern world, and I'll tell you about that in a second. So we went back here to our succession, and starting in the late Carboniferous, that's Pennsylvania, that's tens of million years before that early Permian, that Permian-Triassic extension, we had that very prolific carbonate factory around. All of that blue stuff here is just 2 kilometers of carbonates, so rich in fossils. There's not a rock that does not contain fossil, algae, corals, bryozoan, brachiopods, you name it, all kinds of daisy-clad algae, green algae, red algae, just unbelievable. It's so rich, and it's huge, right? And here's a good example here. We've got all these shelf cycles here going to these massive shelf carbonate reefs, right? You see, you're looking at about 600 or 700 kilometers of 7 meters of rocks here. It's just an amazing carbonate factory, and this is what you see in thin section. All these fossils here, this is incredibly rich as anywhere else in the world for that time interval. But by the late Permian, We still have a shallow shelf, but as you know now, that shallow shelf was chert, it was sponge spiculed, and nothing but these tiny little sticks. What a change. Think about it. You went from this to that, right? If that doesn't wreak environmental devastation, I wonder what would, right? Because it's exactly the same environment, shallow shelf as the previous one, but it's just one that no longer was able to support calcite carbonate secreting organisms. So how do you explain that, right? Well, it's something that I've been working on ever since my PhD. And for many years, I've been interpreting this as resulting from a cooler trend in the Sverdrup Basin, from going from very warm to very cold. But that idea, that juvenile idea I had, just doesn't hold anymore, because we know at that time it was global warming. The evidence is everywhere around the world. It was global warming. Just think there were big glaciations in southern Pangaea, we call Gondwana, in the early part of this, and at the end there were coal measures in Australia. You know, the coal industry in Australia was very highlighted, like 80 degrees south, but there were forests there. Same in Siberia. So the world was getting warmer. So we cannot invoke cooling of the world. So we've come up with another alternative, which is ocean acidification. And you know that right now we're pumping CO2 like crazy, driving our cars and everything. And as we pump CO2 in the atmosphere, it goes into the ocean, transforms itself into carbonic acid, which is the acid you have in your Coke or your pop, which itself breaks down into a number of components, bicarbonate, carbonate, but most importantly, hydrogen. And the more hydrogen you have, of course, the lower your pH, and therefore the lower your the higher your acidity. And carbonates and acid water don't work well together. They dissolve carbonates, right? It's well known that this acid material will dissolve carbonate, and therefore you have a rise of what we call the saturation horizon, which is called lysocline. And we're seeing this right now in our very world, before our very eyes. This is a big problem. In my opinion, the biggest problem with our climate change issue is not that much what's happening in the land, it's what's happening in the ocean. And if we're not very careful, we're going to kill literally the ocean, certainly kill all its carbonate secreting organisms. But that's for another talk. But anyway, well, you know, there's the reefs, but also these little guys, these are coccolith, there's also pteropods. Those in the modern world are very important component of the biological pump. They sequestrate carbonate at the surface and dump it deep in the ocean. The day we cannot precipitate these little guys, we're going to be in deep trouble, and the global warming will accelerate very quickly. But not to worry, I'm not going to talk about this today, but using those kind of ideas, we say, well, can we apply this to the distant past, to the late Permian? So we came up with a model. Again, this is a time series here, where you've got that boundary here. It's called the lysocline, which is really the limit of calcite saturation, and then you calcite compensation depth, which is a bit like the snow line against a mountain here in the foothills or the front range here. And it's really the boundary below which all calcium carbonate organisms or precipitate or whatever will be dissolved. So below the CCD, you've got no carbonate at all. So we got a time series here from the Pennsylvania all the way to the Permian-Triassic boundary right there, where you actually, you know, raise your lysocline through time. And by the late Permian, the lysocline was very high. That calcite compensation depth was right above the shelf. Therefore, nothing, you know, could build skeleton there. And if one was lucky enough to build one, it would be immediately dissolved anyway in that kind of very acid soup. So that is the model here. And just to take you quickly to some of them here, this is Pennsylvania here. So you can see the lysocline is very low, and then it starts rising in the earliest Permian here. And then by Congorian time, it's quite high. And you can see here, you're starting to get that shallow chert here, that white colored chert. But you still have carbonates here. But at the time, this is the late Permian. By the time you get to the late Permian, no more carbonates. The whole thing is gone. And it was very acid environment. Now, there's actually, I lied, there are a few rare fossils associated with that chert, but they are phosphatic nature. And one of them is called Lingula. This is a brachiopod, inarticulate brachiopod. You can see it right there. The bluish color tells you it's phosphate, not calcium carbonate. This guy is still living. It's the oldest living fossil that we have. It's still living in the ocean. It's the most resilient organism that exists. And no surprise, it could live in acidic, hard conditions, because first of all, it builds a skeleton out of phosphate, but also it digs a little hole, and it can kind of create its own microenvironment. And it's still around with us. Not very common, but it's there. And it's an amazing beast. It's been there for over 500 million years. So there it is. So there it is. The whole thing along Northwest Pangea is amplified. Like you get all that chert here, and we believe we have pretty low pH water all around this. And some critic of our models often say, well, how come you don't see that around the world? And the answer is because in western margin of the continent, a thing we call upwelling, which should bring these acidic water onto the shelf and create conditions here that are amplifying a phenomenon that was global. By the way, right now in the modern world, west coast of Vancouver Island, there is upwelling of acid water to the point that organisms that secrete in aragonite skeleton, right, are in deep trouble. They are starting to dissolve, right? So we are right now near the shoreline, west coast, Vancouver Island, because of upwelling of acidic water near the limit of aragonite saturation. And it's just going to get worse and worse and worse. You can just think what it does to shellfish, right? All right. So how do we explain all of this? That's always a big question. It's a complicated thing. Here I have to talk about the carbon cycle. I'll try to simplify this. The whole world, you know, has a very complex interaction between the lithosphere, the biosphere, the hydrosphere, and so on and so forth. And one big component of this is called the silicate weathering buffer. And when you have a mountain, like the Himalayas right now, there's weathering. There's a transformation of those feldspar and minerals that you get from igneous rocks and metamorphic rocks. And as they weather with the atmosphere, they absorb a lot of CO2. So it's a big sink of CO2. It absorbs, it's like a vacuum cleaner. It takes CO2 out of the atmosphere, and then it transports it through the river into the ocean as bicarbonate. So in the late Carboniferous, we had Pangea came together, right? Pangea is that big supercontinent, and it's the collision of Gondwana with Laurentia with Eurasia. You know, the big mountains form all around, including the Appalachian, also the first phases of the Alps, the Variscan orogeny, Hercynian, and so on and so forth. And so there was big mountains here near the equators with ideal conditions for silicate weathering. You throw a bunch of bicarbonate in the ocean. It reacts with the calcium and the carbonate in the ocean to create a very good carbonate factory. In doing that, you maintain your global temperature low, but also your partial pressure of CO2 low. No wonder we had glaciation in southern hemisphere at that time, because all of this was driving the system towards low temperature. But with time, as you eroded those mountains, because over time mountains erode, and because it was Pangea all coming together, there's no more mountains being created, all of a sudden you got rid of your biggest engine of silicate weathering, and which could no longer take CO2 out of the atmosphere, therefore no longer promote carbonate precipitation here, and the ocean tried to buffer itself in raising, you know, its calcite compensation depth, and as a result, the zone, the area of carbonate accumulation became narrower and narrower and narrower, and the zone of silica or chert accumulation became wider and wider and wider, and this is what we see in Northwest Pangea. We published this earlier this year, and it's fairly well received, I might add. All right, so one interesting aspect of all of this is that it did not happen over time. It happens with tens of millions of years. Maybe it started 25, 30 million years before the Permian-Triassic extinction. So that's what I mean, the lead up. I mean, the whole Earth system was pushing the biosphere towards a cliff. No doubt about it, right? Closer and closer and closer to a big, big disastrous event. And you can see that here's those 5 big extinctions. But then there's one here, a smaller one, called the end-middle Permian extinction. And really, you can see here, sure, we have a hell of a peak at the Permian-Triassic extinction. But then you've got, you know, a series of increasing rates of intensity of extension from essentially the Carboniferous Permian boundary all the way to the middle Permian. And there's a little drop, and then it shoots right up at the end Permian extinction, right? So this supports the idea that the oceans were becoming more and more acid, and that it was harder and harder and harder for calcite-secreting organisms to thrive, let alone evolve and flourish. All right? All right, so this part, in summary, the oceans were under increasing stress prior to the massive extinction event due to anoxic condition and acidification. Those two things, the ocean becoming less and less rich in oxygen, and then more and more acid, those two things push the whole world towards a cliff, right? And then what? Then the amalgamation of all the continent of Pangea is to a large part responsible, the breakdown of silicate weathering, global warming, sluggish thermohaline circulation, which leads to anoxia and euxina, and the early to middle Permian extinction. So a lot of bad things were happening before, with just the lead up. That's why we call it the lead up. So as you can imagine, the stage was set for a big one, right? So was the world going to turn around and then improve? Or was it going to just fall over the cliff? Or was something going to push it over the cliff, right? These are essentially the three options. Well, something pushed it over the cliff in a big way. And that something is a catastrophe. It's the largest volcanic eruptions in the history of our planet. The Siberian Trap eruptions resulted in tens, if not tens of kilometers of basalt flows in Siberia over an area that's absolutely mind-boggling. This is Siberia here, and this is the areas of the Siberian Traps here, or you've got here as well, big bullseyes here. This is a huge eruption that lasted probably 1 or 2 million years, and people have been dating it dead on with the latest Permian-Triassic extinction. So as the world was already under stress and duress and ready to fall off the cliff, this came and pushed it over, right? And you can just imagine a big eruption like that puts a lot of CO2 in the atmosphere in a world that's already warming up, puts sulfur in the atmosphere in a world that's already toxic, right? But one thing that it did, which was kind of not neat but interesting, these volcanics actually ignited the coal that had been deposited before in the late Permian. There's a lot of late Permian coal in Siberia, and as these magmas came through the coal, they ignited the coal. So it just added so much CO2 to the whole global budget that it actually went berserk, right? And but until recently, there was actually no proof. I mean, there was a neat idea that, you know, that the volcanic eruption had ignited coal in another, and certainly in there you can see evidence of charcoal, right? But nowhere else in the world had people see any evidence of this. And this is one of our finest paper. It was published in Nature Geoscience a couple of years ago, and we found that I've got to give credit to my colleague Hamed Sane, an organic petrologist with the Geological Survey of Canada, who's actually a specialist, believe it or not, of environmental matters. He studies the stuff that comes out of coal plants, smokestacks in Alberta. That's what he does, right? Anyway, so we gave Hamed some samples from Buchanan Lake. That's our beautiful section. And Hamed looked at the organic matter in there. So they have a very fancy microscopes and instrument to isolate pieces of organic matter. And you can see them here. They all have names. I'm saying I'm not even going to attempt to do that. But he said, my God, what you guys have is identical to what we have coming out of our smokestack in Alberta right now in the modern world, right? And it's called fly ash, right? It's just as those things come out of this, we're burning coal. As you know, most of our electricity in Alberta is we're burning coal to do it, not hydro, not diesel, not gas. We're burning coal, lots and lots of coal. And of course, there's worries about environmental issues here. So people study what comes out of the stacks. And this is what comes out of the stack, these various features here. This is modern world. This is what comes out today as we speak out of the smokestacks in the coal plants. This is what accumulated 252 million years ago in Buchanan Lake, the Arctic. Clearly, and the only way you can get these here is in burning coal. So the Siberian Traps, we had to prove the smoking gun here, the Siberian Trap did ignite the coal, and now because you're in the mid-latitude here, the westerly winds just took that fly ash and zoomed it all around the world and finally deposited here in northwest Pangaea in the Sverdrup Basin. That paper, we're very proud of it, the magazine Quebec Science actually named it top 10 discovery in all fields of science in 2011. So we're extremely proud about this. And Steve and Ahmed have received one of those Jubilee Medal for their contribution to this. And they certainly did most of the work on this one, and they deserve the credit. Amazing discoveries. But we didn't stop there, and Ahmed did not stop there. And then we look at, we say, okay, listen, right now, one thing that comes out of our smokestack in Alberta is mercury. There's a lot of mercury. It's a big concern, right? Because mercury, once it gets in the environment and food chain, it's one of the most toxic things that you can imagine, right? You don't want this in your bone, in your flesh, in the fish, in the food chain. You just don't want mercury, right? And but so there's concern. So Ahmed again is used to measure mercury levels in the modern sediments, right? And so he said, well, let's measure mercury levels here at that boundary, right? And of course, we said, well, if we're burning coal there, you know, there should be quite a bit of mercury. And not only that, the two major sources of natural sources of mercury in the world is coal, and the other is volcanic emission. So all of a sudden, we had in the Siberian Trap both. We had volcanic emission and coal. Therefore, we should see, we were, you know, that was our hypothesis, a mercury anomaly. And guess what? That's exactly what we saw. So here, this is the total organic carbon. These peaks here are those, what we call the fly ash loading events. It's when the Siberian Traps erupted and brought a lot of those fly ash into the basin. And then we look at mercury, Hg mercury, and you can see here, you know, it goes from very little, and then it peaks 3 times here, and then it's really, really high at the latest Permian extinction, and then it decreases again, right? And then we have another thing here. We compare the TOC, that's total organic matter. So it's the organic matter because in the modern world, it's known that mercury is kind of sequestrated by organic matter. The living thing, you, me, your fish, your cat, whatever, this is where it goes. And that's why there's concern, right? But the organic matter is a big vacuum. You just remove mercury from the ocean. And you can see for the longest time, you've got a ratio that was essentially you know, very, very, very low of mercury to organic matter. It means the organic matter was just able to sequestrate, clean the ocean of whatever mercury was coming in. But then there was such a massive loading of mercury at the late Permian extinction that the organic matter could no longer do it, and you can just imagine what it did to the environment. Just a massive, massive mercury we've got in the Sverdrup Basin, but presumably around the world. So we've added in another paper yet a completely unknown possibility as a cause of the extinction, mercury overload. All right. Finally, with all that CO2 in the atmosphere associated with both the volcano and the burning of coal, we already had a world that was getting warmer, right? I told you that the coal measure and all of it was already getting warmer. It was already a bit of a runaway greenhouse going on. And all of a sudden, you add all this stuff, you know. Well, some people calculate that the CO2, like right now we worry about an increase in CO2 about 33% over pre-industrial times, right? We keep hearing about the doubling of CO2, right? Which would happen in about 100 years or maybe 50 or something like that. Well, it is worrisome. I'm not belittling this. But get this. Some people think that across the latest Permian extinction event, CO2 went from values that were about 3 to 4, 5 times modern values. And some people think that pretty much overnight, geologically, it raised 30 times modern value. 30 times. That's 3,000%, right? And we see that here. This is a very complex diagram here. I just wanted you to emphasize here. And we have some very good solid evidence that across this boundary here, the temperature increased dramatically. Really, really dramatically. We went from fairly cool water shelf environment to warm water, tropical light, like overnight, over extremely rapid time. So I'm not going to go through the rest of the diagram. It's too complicated here. You also have no time. But the key thing we see here, this is the Permian-Triassic boundary here on Ellesmere Island. You can see the change in color here from green. That's because of glauconite, a mineral that indicates very low sedimentation rate. And then you've got the arrow here showing all these red beds here. These are what we call caliche, or they're warm, they're hot, you know, arid soil. You know, the world was changing rapidly. You can just see that all dramatically the world has changed here. And here is our chert here. This is in the foreground here, the chert, that white chert. And then you've got, again, the boundary right there, and above there's no more chert. Mind you, there's a big clastic influx. Here's 3 people here collecting ammonoid for scale here. Beautiful outcrop in the Arctic here. And when we look at the boundary here, you see all that chert here. Here's the contact here. And then in here, right above, we have carbonates. So there's a return to carbonates, interestingly. You make thin sections here. You look at what you have. And you've got some carbonate here, some strange little fossil that I can't identify, some microbial fabrics which find all around the world, some remnant spicules here, and of course all the pyrite here that you can see here. And so how do we get carbonates back all of a sudden, right? We had no carbonates for tens of millions of years. All of a sudden the carbonate comes back instantly, right? And this is where Steve at the brilliant idea said we should model this. We put some equations there in a computer and threw some numbers and all of this. So this is ocean pH here, and we believe with time the pH of the ocean was going down. In other words, it became more and more acid. And here's temperature. We believe that across that latest Permian extinction, because of all that CO2 massive influx, temperature must have gone up very dramatically. So we were able to shift the carbonate system, which was by now below calcite saturation, back, not only above calcite saturation, but aragonite saturation. So even though we were destroying pretty much every single habitat, we were able to bring carbonate back. And this is, here's an example here. This was in the late Permian here. You see, that limit of calcite saturation was very, very high, and in the early Triassic it was very low. So it went from this to that in a flash. And it's just not in the Sverdrup Basin, it's around the world we see that. We see around the world, in Europe, in the US, we see growing on the seafloor, the former seafloor, aragonite fans. All of a sudden, all that water wanted to precipitate carbonate like crazy, and it was precipitating right out of seawater, forming huge fans that have bewildered scientists for years, but we think it's because of that very massive, rapid temperature increase that led to this. All right, so in summary here, the Siberian Traps eruption ignited the cold measures, which led to catastrophic global warming, mercury poisoning, and probably a whole slew of other toxic effects, as you can imagine, right? All right, so what happened next? Well, here's the dogma. People think that for the next anywhere from 4 to 8 million years, life was not able to recover. And they have a good point. There's very little in terms of good carbonate factories or anything like that following the late Permian-Triassic extinction. But people have started to look in more detail now, and we're finding a somewhat different story. And our story is that life tried to recover several times, but those efforts were aborted several times over the span of 5 to 8 million years. And here's more work that we've done here. This is a Smith Creek, and this time we're studying here the early Triassic. Here's those stages that Tim Tozer has defined, Grasbockian, Denarian, Smithian, Spathian. So you're now in the early Triassic. This is the Permian here, Buchanan Lake. So put 2 sections on top. Again, you see our various excursions here. Again, this is stable isotopes here. The big, negative excursion across the late Permian-Triassic extinction. But look at above that. We have massive swings of the isotopic record here. Some of the largest shifts in Earth history, really. And that's something that's been reproduced all around the world. So we were just able to reproduce exactly the same, which tells us, yeah, we're in the right interval. So there's nothing magical about it, except we were doing it in organic matter. But the key thing here is our anoxic indicator. Look at that molybdenum aluminum here, one of those that I showed you before. And look how they swing. They almost swing as a mirror image of the stable isotopes, proving there's a perfect link, between those two. And we came up with a model where life actually started to recover, right? And went from euxinic to disoxic and oxic, but oxic conditions were able to be reestablished. But then, bang, it just got knocked down again and again and again. So life tried to reestablish itself, but it was knocked down. So what did it, right? Well, this is where my friend Hamid Sani, again in his mercury, came to the rescue. And he measured in the very same section the mercury content here. And here you see 2 colors of dots, right? You have TOC, total organic carbon, and then you got the mercury, right? And I don't recall which one is red, which one is blue. Doesn't matter because they're identical. They're perfectly in sync, right? What it's telling you is that yes, mercury has loaded like crazy a couple of times, right? And remember, we associate that mercury loading to the volcanic eruption. So this suggests that the volcanoes in Siberia, the big volcano was spitting every so often during the early Triassic. But the neat thing here, the neat thing here is that the organic matter somehow was able to at least for the mercury to buffer the mercury, to sequestrate the mercury entirely, as opposed to the late Permian extinction event where it can't. But nevertheless, there's a clear evidence here that mercury came back in and out, and that can only be done through the volcanoes. All right, so in summary here, successive post-catastrophe recoveries were aborted, mostly due to renewed volcanism and reestablishments of anoxic conditions, right? So this is very new. People thought the whole early Triassic was a bad time. No, now evidence is popping left, right, and center that little pockets of life started, and then they got knocked on the head before they could really take off. Conclusions. This is the end of my talk. All right. So what did you learn today? Well, there's a continuous PT transition in the Sverdrup Basin. There is no basin-wide unconformity, as the giants upon whose shoulder I'm climbing told me, the Dr. Thorsteinson, Nazichuk, Tozer, they were wrong. And that's okay. That's okay to be wrong in science. That's how science moves forward. I'm sure I'm wrong with a lot of things. My students will prove me wrong. Anoxia and Euxina developed over time, but still at the end, there were still broad, shallow areas that remain. So you cannot, as so many people, especially in England, would love, invoke just this anoxic buildup as the cause of the extinction. Forget it. It just doesn't work, right? Now, one thing we put forward is that the ocean acidification put a major stress on the biosphere leading to the extinction. So the whole ecosystem was pushed to its limit, right? Pushing it and pushing it. Those two things working in concert, acidification, anoxia, and stressing life on planet Earth at a time of global warming. So there was significant CO2 increase even before the extinction, right? And then the Siberian Trap eruption, the largest volcanic eruption in the world, were a devastating tipping point. We're not talking, just a little knock, the camel, the straw that brings the camel back. We're talking like a hell of a body check to throw the world over the cliff. And that's what the traps did. It literally led to hothouse conditions. That's very hot temperature and toxic conditions all over, right? And that's enough to me to explain the devastation in a world that was already under stress. And then after that, the recovery that followed was aborted several times, and that provides evidence for renewed volcanism. All right, so in the end, the big question, what caused this, right? What is the kill mechanism? Can we put our finger on one little thing? Well, of course, the Siberian Trap is one big thing, but it's not the only thing. If the world had not been under stress before, you may actually argue that perhaps life would have recovered from the massive extinction. Some people may disagree with that, but I think that's the case. So myself, I think what brought the end of this massive, build-up of diversity and then this resetting the evolutionary clock, you can blame it on Pangea, right? It's when those continents came together, mountains build up, but then they got eroded, and then you change the whole thing, right? So blame it on Pangea. So you've heard it here first. Thank you very much.